balances law problem, the last problem. I'm pretty happy with the results. For the most part, people did pretty well, so I was very excited about that. The problem I promised you on the exam, just about everyone either got it or did really well, so I was very excited about that. I would like to go over the exam and talk about things. Where we're going for Unit 2 is one that I think the students kind of like. This first unit's tough because there's a lot of new concepts that we're not at. This whole idea of flux and fields is a whole different way of thinking about things. What we're going to do here is we're going to finish up talking about going back and forth between this potential representation and this electric field vector representation. I want to talk about that one more time. I want to talk about a little bit, I want you to remember the energy approach, and that's part of what we'll do on the review. The energy approach is the next probably most difficult problem people have in terms of working with. It will show up again on the next exam. I did lecture about it, we didn't hit it very hard on the exam. Then we get to circuits. So we've been talking about static situations. Well, today we'll make that transition into circuits. Circuits are a lot of fun. I think students like the circuits. It's not very challenging math. I think we have very good labs to build up the basis of those circuits. And so this unit will have circuits pretty hard. And then we'll introduce magnetic fields just before the exam. And these will be moving charges. So we're going to move from static situations to more dynamic situations. We'll focus on circuits, which is it's a nice break. Then Unit 3 will go into magnetics, which is really weird. And if you think what we've been doing now is weird, this adds a whole magnetic circuits adds a whole level of odd. And then we finish with thermal, which is more like a lot of chemistry and gas laws. So we're going to take a little bit of a break here after the ugly math. There's pretty ugly math up there, but we will talk about it. Then we'll do circuits, which is very straightforward math. Then we'll hit some very interesting phenomena with magnetics, and then thermal. So, any questions about where we're going and what we're at? All right. So in the back of your mind, I'd like you to think about this as we review. We can represent an electric field with potential. And in some ways, I think of potential as being temperature, because at every point in space, there's a measurement. That's the electric potential. And it's a scalar. Unlike our other representation with the electric field, at every point there's a vector. So in a lot of ways, a potential representation of a field is a little bit easier to deal with mathematically. In the day when computers were a little bit less common, we would often calculate potentials from complex, and then it was easier to calculate the potential of the field, then do these derivatives to find the electric field in terms of a vector. And believe it or not, that was easier. Now with computers, it's just about as easy either. You put your topology in the program and the code spits out what your field is. So computationally, it's not as much of an issue. But in the day, we did calculate potentials first, then do the derivative to find the electric field. Can we review the test first, or do you want, there's one more thing I want to talk about here. This first? All right. So, if we let's talk about problems, I think 11 and 12. The test, and I think it's a good way to bring this up. 12 and 13. 12 and 13 were the same problem. What the 12 was, an electron is to be accelerated from rest to 7.26 times 10 to the 5th meters per second in a uniform electric field. The electron will leave the field after 10 centimeters. What is the magnitude of the electric field? So we have an electron with a negative charge, and I'm going to assume that it's accelerating in that direction. So there's some F net, F on it, that will be equal to Q times E. And then, which direction is the electric field? Must be in the opposite direction, right? So that would imply there's a positive plate here, negative plate perhaps if this was set up by a capacitor. Might be some grate. And this electron is going to be accelerated for 10 centimeters. And then it leaves the field. So you can imagine maybe there's a grate here, they're 10 centimeters apart. This will start at rest, and it will accelerate, then it's out of the electric field. We know that V initial, 0, V final equals the easiest approach to this problem is to approach it from energy. One person did that. And I expected you to do the kinematics. If we look up here, since we have a uniform electric field, the change in potential here will be the integral of the electric field time over the distance. And that dot product is -1 because they're in opposite direction. So as we integrate from here to here, so our delta V will be equal to E times V equals, right? So that's 10 centimeters. And we have conservation of energy. Our initial kinetic energy is 0. Our final kinetic energy, if we also know it, because we know our final kinetic energy. We know that our change in electric potential energy will be Q times V. So we can now set up our conservation of energy. We have our initial kinetic energy, zero, equals our final kinetic energy, plus our change in electric potential energy. Everyone see that? So we have our initial kinetic equals our final kinetic plus our change in potential energy. I could have, some people said on the next part, no, we'll talk about that later. Delta D. Which is equal to this point in time, we know the mass of the electron, we know the velocity final, we know the charge on an electron, E 1.6 times. We don't know E, and we do know V. So we can now solve for E. All over E times V. We can substitute in. And we find that that was equal to 15 volts per meter, or newtons per coulomb. Now, only one person approached it this way. That's okay. Not the way I wanted you to. It's not, actually, I would have loved to see you do it this way, but it's not the way I expected you to because I hadn't pushed this. So let's look at what's happening here. As we move towards the positive charge, the potential goes up. We look at the rate of change of that potential, it tells us the electric field. So that is an application of this situation up here. As we move through the electric field, the voltage goes up. If we move in line with the electric field, we change potential energy, we change kinetic energy, assuming we have no loss. So if we move this direction, potential would go down. If we move this way, potential moves up. So if you think about the electric field lines, they point in the direction of down for a positive charge. Any questions about that? What was the other approach? The other approach was F. Let this be I direction equaled Q E I hat. And we need to define the accelerator. That's also equal to mass times acceleration. And that was all in the x direction. So we could say in the x direction, Q E equals M. We want to find E. We know Q, we know M. If we could find AX, then we could find E. So let's see, we know the initial velocity, we know the final velocity, we know x0, 0, x final, 0.1 meters. We said acceleration unknown, change in time unknown. We want this. We know in final and initial position, we know the initial and final velocity. We look at our kinematics equation. We know that v final squared equals v initial squared plus 2a delta x. We can now solve for a, see, v initial is 0. We solve for ax equals, and this is d, ax was equal to v final squared over 2 d. We substitute back up into here. We solve for e, and we get the very same relationship we just had. When we come to q, e equals m, v final squared over 2d, or if we divide both sides by q. We end up with a negative sign on E, because Q is negative here. What does that tell us? It tells us the electric field is pointing in the opposite direction. They wanted the magnitude that was important. But notice you get the same answer both ways, both from the energy approach and the kinetics approach. Any questions about those? So the field strength here is 15 volts per meter. It's 10 centimeters apart, or a tenth of a meter. What's the potential difference between these 2 points? The voltage, the electric field is 15 volts per meter. That tells you how fast the potential is changing. So if we want 1 meter, wouldn't the potential be 15 volts? If we go a tenth of a meter, wouldn't it be 1.5 volts? Look at the next problem. The next problem says, an electron is to be accelerated from rest in a uniform electric field The electron will leave the field after the potential has increased 1.5 volts. So it's the same problem. I just expressed it a little bit differently. Instead of asking for the electric field, I want to know what the speed is when it's going to leave the field. Guess what the speed is going to be? It'll be that. All right. So, how do we solve it? Again, this time we take an energy approach. We say the kinetic energy initially is 0, plus the kinetic energy final, now we don't know it, plus our change in potential energy, which will be Q times delta V. So we have our kinetic energy initially, 0. And so now we just solve for V final. Pretty much the same thing I showed before. We started, and you find out it's equal to that.
I have a question. I'm not sure if it's even a legitimate question or not, but when we're looking at this and it's inside the field, initially, doesn't it have some sort of potential energy initially then?
It does, and that was where some students approach this as 1/2 m v initial squared plus q v1 being a potential equals 1/2 m v final squared plus q times 1.5 volts plus V1, because it's now 1.5 volts higher than V1. What happens here? Let's V1. Can we cancel the QV1 on both sides? It's a very good question, actually. I meant to comment on it. That's why I like this change in potential approach a little bit more, because I can eliminate that step. This is correct. It's just I'm lazy.
I was just curious just because I was thinking, because it says, didn't it say it like leaves the electric field or something like that?
It leaves the electric field. Imagine what we've got here is a capacitor, except instead of those plates being solid, there's either a hole in them, which doesn't significantly affect the field, and the electron starts right here, and it accelerates through, goes through the 2 holes and comes out. The other way they actually achieve this is they'll make screens, and there's holes in the screens, and most of the electrons make it through the 2 screens.
I was just curious just because it seems like there would be no electric potential on the outside of the thing once it had left.
Exactly. So what happens is, it starts here, it goes through the electric field, then it leaves the field, and it's accelerated between the 2. It doesn't accelerate anymore once it's out.
Okay, but we can't, like on the latter half of that equation, we can't cancel out the Q 1.5 V or something like that because it's 0 once it's left?
Oh, that's another good question. What's the potential on this plate? Let's just say that that's potential V1. This potential here is V1 plus 1.5 volts. What's the potential over here? What's the potential over here? What's the potential right between those 2? So before we go that, what's the electric field here? 0. What's the electric field here? The electric field here is 15 volts per meter. How much work do we do moving the electron from this area over here with the electric field 0? zero work. So the potential energy here is all the same, right? So the potential everywhere over here must be V1. Everywhere over here the potential is V1. We go back up to here, as we integrate that value, electric field is zero. So in terms of the math, we're integrating zero, so there's no change in potential. In terms of energy, which is really the way I'd like you to think about it, it doesn't take any energy to move the electron over here. So the potential must all be the same. Here it takes, we actually gain potential energy as we move there. It takes work to move it this way. It actually takes work to hold it back as we move it across that way. So here, the potential is going up. Potential energy for the electron is going up also. The electron's potential energy is going down. So this is what I really want to emphasize as we go from here to here. The electric potential goes up. The potential energy for a positive charge would go up, but the positive potential energy for a negative charge goes down. Then when we get out here, the electric field goes to zero. Every place over here, the potential must be this. What's the potential energy right halfway between the two plates? It's going to have to be half of this. It's a uniform field. 5 centimeters times the 15 volts per centimeter, it's going to be 3/4 of a volt higher than this plate here. So I think your concern was the electric field goes to zero here and here. Doesn't the potential go to zero? And the answer is no. The potential is constant over here, but it's not zero. And those are typical conceptual questions. The electric field is zero. Is the potential zero? No, and the reason we emphasize that is for just this type of problem, so that you don't think that the kinetic energy or the potential energy of the particle changes over here. Right? It's very common confusion. Electric field's gone to zero, therefore the potential's gone to zero, therefore the energy's gone back to maybe this. But it isn't, that isn't what happens. We have this grate, we have another grate. As the electron goes, there's no field over here, it's not accelerated. Somehow we give it just a little nudge to get inside the field. Now it accelerates across, and it's going at constant speed over here because there's no force on it. In terms of potential energy, the potential changes from here to here. So the potential energy of the electron changes, its kinetic energy changes from here to here. And once it's out, there's no change in potential, so there's no change in potential energy. So if it's a conservative field situation, then the kinetic energy will change.
So did you say it's kind of different than like kinematics or something, or like conservation of energy with gravity because you're adding both potential and kinetic energy?
The situation here, in terms of gravity, would be, imagine a long flat table, then a ramp, even ramp where this is straight, and then a long flat table again. So the ball's here, it has a certain potential energy. And if I move it back here, its potential energy doesn't change, right? That's like moving the electron over here. If I nudge the ball so it goes over the edge, it will accelerate down the ramp. And then it will roll at a constant speed. So that's the gravity analog to this situation.
But we said that the potential is greater on the right hand side, so wouldn't it be like, is that because it's the negative charge?
It's because it's a negative charge.
Okay.
Imagine the problem with charges is
basically just went uphill.
Imagine this situation for a positive mass, right? The potential goes, that height elevation goes up and the potential energy goes up, but the kinetic energy goes down. But now we have this funny negative charge thing where as the potential goes up, the potential energy goes down because there's that negative charge. So that's where it's a little bit hard to wrap your head around it, because it's like what's uphill for one charge is downhill for the other. That's where that analogy kind of falls apart, because there's positive and negative charges that are not positive and negative masses, in my understanding. These are good questions. This math actually takes that into account. What it's telling us is the rate of change of our potential. That's telling us how steep the hill is. The stronger the electric field, the steeper the rate of change of the electric field, the faster the voltage changes as you move a distance. That's what this tells us. If we look at how fast it is changing, and then we look at it over distance, we can see how much the potential has changed. So that's why I wanted to talk about these problems, tie in with this concept. If you go back through the notes, you look at the text, there should be an example of going from a point charge. We can go from the electric field, we can do this integral to find the potential, or you can take the derivative to go from the potential back to the electric field. So you should be able to do the same thing inside the capacitor. And in theory, if I gave you an arbitrary mathematical description for the electric field, we should be able to go from one to the other. In our lab tomorrow, what we will do is we have some paper that's a very weak conductor. We will put 2 dots on the paper. One will be at 20 volts, one will be at 0 volts. Then what we're going to do is measure the potential at different points on the page. And you'll find all the places where the potential is 5 volts, and all the places where the potential is 10 volts, and all the places where the potential is 15 volts. Once you know the equal potentials on the paper, you should be able to graph the electric field. But what do we remember about electric fields? If we move a particle, think energy, if we move a particle along an equal potential, let's just say this is all at 5 volts, and this is, say, all at 3 volts. If I move a particle from anywhere along this line, how much work does it take? None. So the electric field must be perpendicular at all those points, right? So we know that any point here, the electric field must be perpendicular. Same thing here. If I move anywhere along that equal potential, no work, so the electric field must be perpendicular. If I go from the 3 volt potential line to the 5 volt potential line, and I have a positive charge, do I have to do work? Is that positive or negative? As we go to higher and higher voltages, what are we approaching, a positive or negative? Positive, so it would take work. So our electric field is going in which direction now? Going away from the positive. Towards the negative. So our electric fields go down towards lower and lower voltages. They are perpendicular to equal potential at every point. So we can now graph how somehow we've created a field, and I'm just guessing from what I've drawn, something that's perpendicular here and perpendicular there, what the electric field must look like. So you should get it, you get a feel for what's happening. And this will be our goal of our lab tomorrow. And this is a representation of that math. We move along one of these equal potential lines, the strength of the electric field times that distance gives the change in potential. So, is the field stronger here, at A, or at B? What's your guess? How does the distance between the 3 volt and 5 volt equal potential line compare at A to B? Is it a little farther to go from the 5 volt to the 3 volt at B? This is a straight line, right? And this is curved like this, and now this is a curved line. Wouldn't this be a farther distance? So the field would therefore be weaker. So the electric field lines are closer together, electric field's higher. For equal potentials are closer together, field is higher, because we're changing potential more quickly. Does this seem a little esoteric? It's really hard to represent and understand these electric fields. We really struggle to get a visualization of them, and to really get a visualization of what does this really ugly math mean. So that's what we're trying to achieve in the lab tomorrow. It is hard. I encourage you to work at it. It really does give you a strength, a sense of what those fields are, and that's a very hard thing to do. Deep breath. We'll get to circuits, right, which I promise are much more concrete, much more straightforward. But I do want to try to wrap up here. Shall we go to the last problem on the test? Actually, I'm going to step back. I'm going to do one other problem. The reason I want to do this other problem is because one person approached this test, this problem, in a way that I just loved. And that was problem 11. And it lends itself well to going to the last problem. We have a long wire. There's a positive 2 microcoulomb charge. Distance is 3.8 centimeters. And the force on this, is the force of attraction, wasn't it? Equal 5.4 newtons. We also know that that's equal to Q times E. And the question is, what is the charge on 5 centimeters? This is that wire. Remember that one? So the way most people solve this is they said, well, the electric field here near a wire is equal to K times 2 lambda over R. R was equal to, is that right, meters? See, we know, and then Q is equal to 2 microcoulombs. So we can find lambda pretty quickly. we then find lambda is equal to F divided by Q, K, 2 times R. Isn't that right? Then the charge on 5 centimeters wire equals 0.05 meters lambda. And that is equal to now, that's nice, and it's really the way I expected I to do it. One person had another approach, which I really, really liked. This person did this. By the way, I gave a bonus point if you did the signs correctly. I did everything in magnitudes, and I end up with a positive charge. If you do things correctly, let this be X. This becomes a negative 5.4 I hat. And you end up with a negative charge here, which is what you should get. And so if you solved it the way I just did it, I give you full credit. If you added the negative sign, I give you a bonus point because that's really the right way to do it. But what this person did, and I really, really liked it, is they said, let's imagine a cylinder. It's 5 centimeters high. It's got symmetry, so the electric field's coming out. And the radius here is 0.0388 meters. The area of the outside of that cylinder will be equal to a height here times the distance around times 2 pi times the radius. Then you can apply Gauss's law now, because we now have 5 centimeters of charge times Q, right? Times lambda. So we have Qn over epsilon naught equals our flux. Our Qn will be H times lambda. Epsilon naught is epsilon naught. Our flux is equal to E times A. Actually, what if I remember what they did here? Oh. They did one other thing. They said F equal QE, right? So here they said this is equal to E times A, which is equal to, and they said E equal F over Q times A, which is equal to H 2 pi R. Now we know F, we know Q, we know H is 5 centimeters. And we know 2 pi, we know R. You can solve it. So you apply Gauss's law, which is beautiful. So, I love that way of approaching it because that just shows a lot of strength in understanding the application of Gauss's law. It shows the symmetry, and it's just a great way to apply Gauss's law. And they never worried about, they never did this. They just left that Q inside, and they solved for it. They never found the charge density in the wire. So you just multiply now, Q enclosed equals F epsilon naught H 2 pi R all over Q. And you end up with the very same answer. So I found it particularly elegant because they never bothered to find what the charge density of the wire was. Does everyone see how that was done? So that, I like that a lot. And I like that as an introduction to the last problem, because the last problem was where I wanted you to apply Gauss's law. We have some thick plate. Well, it may not be thick, but it's got a thickness of D. Now, imagine this is in the YZ plane. So this is a very large, thick plate. I wanted to know what's the electric field inside the plate. So by symmetry, I'm going to draw a line down the middle. And I was going to call that the YZ plane. There's our X. And I'm going to build a box right in the center of that plate. And I think that's the thing that most of you struggled with. A lot of you tried to build the box all the way to the outside. To find the electric field inside the plate, we need to find a surface, a volume, that's enclosed in the plate. By symmetry, the electric field lines still go out. We know that outside the plate they're uniform. But inside the plate, the field's probably going to get weaker and weaker and weaker until we get to the middle, because think about it, the electric field's going out this way, going out this way. There must be some transition in the middle. And just like for a spherical volume, when we have the charge density inside, as you get closer and closer to the center, the field goes closer and closer to zero. So on our cube here, I assume that this cube was L by L by L, or volume. We're getting a lot of V's here. Equals L cubed, area, L squared. Does everyone see how I've set this problem up? Is there any flux out of the top, bottom, front, or back? It's a very large plate. By symmetry, electric field lines are going out from the plate. Does it make sense for them to be going along the surface of the plate? So, by symmetry, top, bottom, front, back. But E does equal 2A times Z from this side right here. Another side over here. So there's two areas. The electric field is perpendicular. So that will go 2L squared E times 2L squared E. Yeah, thank you. Q enclosed will be equal to rho times volume. Rho L cubed. Now we apply Gauss's law. Let's go the other way around. So our flux now is 2L squared P equals rho L cubed over epsilon naught. Solve for E. L squared cancel. Rho L over 2 epsilon naught. If you got there, I gave you full credit. If you want to go one step further, call this distance R. Say 2R equals L, or R equals L over 2, in which case E is equal to, you substitute here, rho 2R over 2 epsilon naught.
R,
And do-
rho R.
What's that? Rho R, thank you. And then to make it perfectly into a vector, rho is out to the right. You can actually replace this with the vector equals rho x I hat over epsilon naught. When x is positive, E is in the positive x direction. When x is negative, it would be in the negative x direction.
I'm just curious, if it's like you're saying like it's a large kind of block or that sort of thing, the thing that we're measuring?
It's a very large plate.
Yeah, like,
Right.
why would there be no charge coming out of the top or the bottom of that?
It's like our infinite plane.
Yeah.
So why would it point up rather than down?
Well, I can understand if it's an infinite plane, but if it has a thickness, then it has some, I would think that it would have like width, so there'd be field lines that are coming out like the sides and the top, because.
But what we're saying is it's so big that we're not anywhere close to the top or the bottom. The top or the bottom is very large in physics means treated as infinite. Yes, if you get to the edge of the plate, all bets are off.
And sorry, one more question. If you don't mind.
No,
But,
that's fine.
for the cube, if it's like a really large plate going in one direction, I think it's like the z direction, but it's like the large plate going in the z direction, and we have the cube on there. Does it have to be at the center of that distance?
It has to be at the center because by symmetry, what's on the left has to represent what's on the right. If we put this cube here, Gauss's law still applies, but now there's flux coming in one side and going out the other.
But on the other plane that goes like into the board,
Yes.
it has to be the center of that direction too. Is that
We're assuming that it's so large that it's like the center for the vast majority of the distance. So, yes, if it's a finite plate, for it to be perfectly true, it does have to be centered. But we're thinking about this being so large that we can treat it as being infinite. Are there infinite planes? No. Are there infinite slabs? No. But to analyze them, we apply Gauss's law, we treat them that way. Number 10 was the problem with the two charges and finding the electric field. You guys did great on that. Looks like about 2/3 of you prefer Knight's approach rather than my approach. That's fine. There was some sign errors, but there were sign errors with both my approach and with Knight's approach, so I can't really say that one or the other really is superior. I did not punish those sign errors. So that's the key. I did too much. It was like a point off if you made one sign error. The vector math, most of you did okay. For our hat was the unit vector for R. Some people find the unit vector for E. No, I meant the unit vector for R, not the unit vector for E. A few people found F by Q, magnitude E, R hat. You didn't have to do that. We just needed to multiply Q times E. False is a red ball has a positive charge, a blue ball repels the red ball, the blue ball must have a positive charge. True. Red ball has a positive charge, a blue ball attracts the red ball, the blue ball must have a negative charge.
False.
False. If the Gaussian surface contains zero charge, then the field at the surface must be zero.
False.
That's false. It could be, we could have field coming in one side and field going out the other. We can put a Gaussian surface in the middle of a capacitor. There's zero net charge, but there's definitely field coming in one side and going out the other. So that's definitely false. An excess positive charge is distributed evenly throughout an insulator. As you get closer and closer to the center of the sphere, the electric field gets weaker and weaker. That's true. Again, it's exactly what we're seeing here, except it's inside a sphere. Gauss's law applies to irregular shapes. Yeah, Gauss's law applies regardless of the shape. The force on a positive test charge at point A points down, the test charge is removed. Well, the positive test charge is pointing, the force on it is pointing down, the electric field is pointing down. It's there whether the test charge is there or not. However, if we put an electron there, force on that electron will be up. So the answer is C. A dipole in a uniform field. This one troubles people. Think of a dipole as a positive charge and a negative charge. You think of them as being connected by a stick. You think? If it's a uniform electric field, these are the same charge, opposite magnitude. The two forces must be equal and opposite, so the net force is zero. However, if they are separated some distance, is there a torque? Is there a tendency to make it rotate? Yes. There's a net torque. All right, a negatively charged particle is brought nearer to a positive charged wire. As the particle approaches the wire, we're getting closer and closer to a positive charge, so the potential goes up. Since the particle is negatively charged, that means the potential energy goes down. We have one more concept I have here before we go to circuits. Think about this for tomorrow, then we will talk about circuits. Little conductor, big conductor. We connect them by a wire. We put some excess charge on them, and then we separate them. What happens to the electric field? What happens to the potential involved? See you all tomorrow.